Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on December 11, 2025, about 5 days ago. It introduces a system called SHARP that turns a single photograph into a full three-dimensional scene in under 1 second on a standard graphics card, while cutting perceptual error metrics by about 25 to 34% for LPIPS and 21 to 43% for DISTs, and slashing synthesis time by roughly 3 orders of magnitude. The paper is titled, SHARP Monocular View Synthesis in Less Than a Second. And, as we will see, this combination of speed, realism, and true metric geometry could reshape how single photos power virtual and augmented reality experiences. Alright, Figure 1 contrasts synthesis latency with image fidelity on the ScanNet++ dataset. The plot shows that SHARP sits at the bottom left, which means SHARP achieves both the lowest distortion score and almost instantaneous generation. Other colored points represent competing methods that either take tens to hundreds of seconds or produce blurrier images. The brown point on the far right illustrates a diffusion-style model that is extremely slow while still not matching SHARP's fidelity. So while Figure 1 quantified speed and fidelity, Figure 2 shows concrete visual comparisons between SHARP and several competing systems. Each row corresponds to one method, and each column shows a different scene, so the grid exposes how well details survive viewpoint changes. The zoomed white boxes highlight fine structures like frayed ropes, mug edges, and koala fur, which remain crisp for SHARP but tend to smear or blur for the baselines. This side-by-side layout underlines that SHARP is not only faster, but also visibly sharper in small textures. So after those visual side-by-sides, Figure 3 lays out how SHARP turns one image into a three-dimensional scene. The left side shows an image encoder and depth decoder that extract layered depth from the input photo. The center orange block performs depth adjustment, which corrects monocular depth ambiguities. The right side converts adjusted depth into three-dimensional Gaussian points, then a Gaussian renderer produces high-quality novel views in real time. Alright, while Figure 3 explained the pipeline, Table 1 reports how that design performs across 6 different benchmark datasets. The table lists DISTs and LPIPS scores, where lower values indicate more perceptually accurate novel views. Across every dataset, the bottom green row shows that SHARP attains the best or tied best numbers, often by a wide margin. Competing systems like TMPI and Gen3C occasionally win a column, but they never dominate across datasets the way SHARP does. Well, after seeing SHARP's accuracy across datasets, Table 3 compares how large these models are under the hood. The top row lists total parameters, showing that diffusion-based systems like Gen3C reach about 7.7 billion parameters, far larger than SHARP's 700 million. The second row reports trainable parameters, where SHARP needs about 340 million, while some diffusion baselines train more than 7 billion. This contrast means SHARP delivers better or similar quality, with dramatically fewer learned weights, which helps with training costs and deployment. So while Table 3 contrasted model sizes, Table 6 spells out how fast these systems actually run on an A100 graphics card. The table reports 2 numbers per dataset: inference time, to build the three-dimensional scene, and render time to draw one image. SHARP takes around 0.9 seconds for inference and roughly 1 to 200ths of a second per render, which means real-time playback. Competing models often need tens to hundreds of seconds just for inference, and some diffusion approaches take more than 800 seconds, making interactive use impractical. Wrapping up, 2 takeaways stand out. SHARP shows that a single feed-forward network can turn one photo into a metric three-dimensional Gaussian scene in under a second, and it does so with clearly sharper, more realistic views than heavier diffusion systems. This unlocks practical single-image virtual and augmented reality experiences. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.